Hey everyone, welcome back to Trigonometry. This will be lecture 2 of the course, and in this section we're going to discuss we're going to introduce the trigonometric functions, and over the course of the next few lectures we'll introduce a couple of different definitions of the trigonometric functions. We're going to start with what is probably the most straightforward way to think about it, and that's through the unit circle. It's also introducing the trig functions through the unit circle helps to justify the use of radian measure. So we're going to start with that, and so let's go ahead and jump into it. And so we'll call this section 1.2 trig functions and the unit circle. Okay. So what do we mean by a unit circle? So a unit circle is a circle of radius 1. Okay, a circle of radius 1 with its center at the origin of the xy plane. Okay, so it's a circle whose radius is 1 that's centered at the origin of the xy plane. Okay, and so if I were to draw that, right, you can imagine this is the xy plane here. I'll just put x here, and I'll put y here, right? And let's say that that's 1, that's -1, that's 1, and that's -1, right? And so we can just draw a circle here, right at the origin on the plane here. Okay, and so we know that the radius is 1, which means that this is 1. So that means that this point here is 1, 0, right? Okay, and so that is the unit circle. Now this point at the top, that's 0, 1. All right, so let's put that on there too, just so we can make sure we understand this. And this is -1, 0 over here. And of course this is 0, -1 down below. Okay, so this is the unit circle. Now, what we want to start with is kind of tie this into the radian measure. Well, this is a unit circle. It's going to have a particular equation. So the equation of the unit circle is x squared plus y squared equals 1. Right? So we know that. We know that from algebra. Okay, and then remember, in the last lecture, we said that theta was equal to s over r, right? Now, what was s? Well, if I draw any intersecting arc, I'm just drawing it here for convenience, but it could be anywhere on the circle, it's going to sweep out some angle theta, right? And that angle theta, when you sweep that out, you're going to simultaneously sweep out an arc of length s, right? So the length of the circle that goes up to this point is s. Okay, and so theta here, this is the measure of the angle that is swept out by this ray. Okay, now we know that the arc. So if theta equals s over r, then what is s? Well, s is going to be equal to, just do a little algebra, multiply both sides by r. You can see that s is equal to theta times r. Right now, but in a unit circle, what is r? Well, it's a unit circle, so r is equal to 1. So s equals theta times r is really s equals theta times 1, which implies that s is equal to theta. Right? So in a unit circle, the length of the arc is the same as the angle theta. Right? So if theta is pi over 2, then the length of that arc is pi over 2. Right? If theta is 2 pi over 4 or 2 pi over 3 or something, then s is going to be 2 pi over 3. Right? So s and theta are identical in a unit circle. Okay? So s equals theta in a unit circle. And you'll see as we kind of go on that this is extremely convenient, right? For a lot of the stuff that comes up later in the course, having the length s equal the angle theta is extremely useful. Okay, and so this is what we mean by the unit circle. You can kind of think of this as a definition of the unit circle, and also kind of an immediate consequence of the unit circle, and sort of a tie-in with the idea of radian measure. Okay, now let's talk about the trigonometric functions. Okay, so the trigonometric functions. And people will have heard of some of these just in conversation. I mean, not like people sit around and talk about trig functions, but if you watch The Simpsons, for example, or the Futurama or something like that, and they're talking about math, you'll frequently see trig functions like kind of thrown up, and whenever someone's sort of making fun of the pedantic nature of mathematics, like trig functions will frequently get pulled into the joke. But the trig functions, they're fairly straightforward to understand, but they have an extremely, an incredibly central role to play in pretty much all mathematics. And you'll see that they're based on a very simple definition, right? And so I'm going to draw a picture first just so we can reference it in the definition, right? So again, this is just a unit circle. So I've got a unit circle, and on that unit circle I'm going to have some arc, and I'm just going to draw it down here just to be different, and it's going to be in relation to this angle theta, right? And on that unit circle there's going to be some point called P, and P is just a point in the plane, so you can think of it as as having an XY coordinate. Okay, and so this is P right here. Okay, and so if theta is a real number, right, and P is equal to XY, right, is a point on the unit circle, it's a point on the unit circle that corresponds to the angle theta, right? Corresponds just means that theta is the angle that's swept out by the ray that intersects the line, or intersects the unit circle at point P. Okay, that's all correspond means. So if theta is a real number and P equals XY is a point on the unit circle that corresponds to the angle theta, then sine of theta is equal to y, cosine of theta is equal to x, and tangent of theta is equal to y over x. Okay, so these are the three primary trig functions, and so this is the notation: sin theta, cos theta, tan theta. But sin theta is the sine, and it's kind of written in English like this, and then you've got the cosine, and you've got the tangent. So those are the three primary trig functions, and then there's three reciprocal trig functions. So you've got the cosecant of theta, and that's equal to 1 over y, and then you've got the secant of theta, and that's equal to 1 over x, and then something called the cotangent of theta, which is x over y, right? And so these, again, this is the cosecant, this is the secant, and this is the cotangent. Okay? And these are the 6 trig functions. Right? And so you can kind of see, and we'll get into this relationship a little bit more later, but you can see that the cosecant and the sine are reciprocals of one another, meaning that if the sine of theta is y, then the cosecant of theta is 1 over y. And the cosine and the secant have the same relationship as well. So the cosine is x, the secant is 1 over x. Right? And then the same thing for tangent and cotangent. It's just the same. They're almost the same, except they're reciprocal. So y over x for tangent, x over y for cotangent. Okay, and so these are the 6 trig functions. Okay, let's go ahead and do an example. Let's do an example to make sure that we understand this. So let's use some real numbers. Let's say that theta is an angle sweeping out an arc. Sweeping out an arc sufficient to land on p equals -1/2, comma, square root of 3 over 2. Okay. Identify the 6 trig functions for theta. Right, so we're not told what theta is, we're just told that it sweeps out an arc and lands on the unit circle here. Right, so let's draw a picture of what this is. Right, so again, I've got my unit circle here. Okay, and so just kind of looking at these values, I can see the x coordinate is negative, so, and the y coordinate's positive, so we're somewhere over here. Right, so my theta is going to sweep out something like that. It's not important that it be drawn precisely. But this is my p. So p is equal to -1/2, comma, square root of 3 over 2. That's this point right here. It's somewhere over here, right? And so just to make sure we're crystal clear on what this means, it just means that this is the length -1/2. That's the distance on the x-axis. And this is the length square root of 3 over 2. That's the distance on the y-axis, right? Just like a normal xy coordinate. Nothing exotic here yet. Okay, so we just want to know what are the values of the 6 trigonometric functions. Okay, so we can kind of go through this. The sine of theta is equal to y, right, which is equal to the square root of 3 over 2 in this case. The cosine of theta is equal to x, which is equal to -1/2. And the tangent of theta is equal to y over x, right? So in this case, y is equal to the square root of 3 over 2, and x is equal to -1/2, right? So we have to know how to deal with division of fractions, and so we have to remember that dividing by a fraction just means you multiply by the reciprocal of the fraction. So square root of 3 over 2 times 2 over -1. Right, so you can see that the 2's will cancel, and this is just negative square root of 3. Okay, so there's the 3 primary trig functions, their values. What about the secondary ones? So cosecant. So cosecant of theta, we know that's 1 over y, right? And so that's going to be 1 over the square root of 3 over 2. Which means you can think of that as 1 over 1 times 2 over the square root of 3. And so you get 2 over the square root of 3. Okay. We'll talk about this in a second, but this 2 over the square root of 3 is actually equal to 2 square root of 3 over 3. And we'll get to why that is in a second. Right, so we'll address that in a moment. All right, what about the secant of theta? Well, it's 1 over x, so that's 1 over -1/2. So you can think of that as 1 over 1 times 2 over -1, and so it's equal to -2. And finally, what about the cotangent of theta? Well, it's the reciprocal of the tangent, so tangent's y over x, so cotangent must be x over y. Right? And so remember, x is -1/2, and y was square root of 3 over 2. And so this is -1 over 2 times 2 over the square root of 3. And so you see this is equal to -1 over the square root of 3. And for reasons similar to what we see with the cosecant, this is actually equal to negative square root of 3 over 3, and we'll look at that one as well in a moment here. Okay, and so these are the values of the 6 trig functions. Okay, and again, it's just if you're given this amount of information here, it's just as simple as reading off the values. Maybe you got to do a little multiplication or division, but it's very straightforward, right? Okay, very good. So what is going on here? What are we doing here? How did 2 over the square root of 3 become 2 square root of 3 over 3, and why did it happen? And similarly, why is negative 1 over the square root of 3 equal to negative square root of 3 over 3? This is something called, this is kind of a preference in mathematics. We don't like to see radicals in the denominator. We don't like to see radicals in the denominator. Right? That's just a preference. It's kind of like, you know, how if a fraction can be obviously reduced, you should reduce it generally. Right? It's one of those things. It's a preference. It isn't wrong to write it like this, but it's just generally preferred that you write it without the radical in the denominator. And so what's happening with these two steps, from here to here and from here to here, is something called rationalizing the denominator. So let's talk through what that is. Rationalizing the denominator. Okay, and this is just a way of getting rid of radicals in the denominator. Okay, and so I'll give you an example here of how this works. So let's say I have 1 divided by the square root of 2. I don't really like the way that looks. I don't want 1 over the square root of 2 because I don't want a radical in the denominator. Well, 1 over the square root of 2, as you'll no doubt agree, is equal to 1 over the square root of 2 times the square root of 2 over the square root of 2. Right, that's obviously true, right? Because the square root of 2 divided by the square root of 2 is just 1, and you can multiply anything by 1 without changing it. Right, and so let's see what happens when I do this. So when I do this, I get the square root of 2 on top. Right, 1 times the square root of 2 is just the square root of 2. And down below, what do I get? I get the square root of 2 times the square root of 2, otherwise known as the square root of 2 squared. Okay, and when I simplify this further, you can see that this is the square root of 2 divided by, what happens when I square a square root? Well, they kind of undo each other, and so I just get a 2. Right? And so this is what we mean when we rationalize the denominator. Specifically, we want to multiply by a factor like this. Let's do another example. Let's say I have negative 2 divided by the square root of 3. Again, I don't want the square root of 3 in the denominator, but I want an equivalent number. What I can do is I can multiply by the square root of 3 over the square root of 3. Right? And when I do that, in the top I get negative 2 times the square root of 3, and down below I get the square root of 3 squared, and so the square of a square root, because you know they undo each other, and so I have negative 2 times the square root of 3 divided by 3. Right? This is the preferred way to write it, right? But these are equal. Right? You can see that they're equal. Okay, and so that's all that's happening with these. So in the case of this one, I multiply the top and bottom by the square root of 3. In the case of this one, I also multiply the top and bottom by the square root of 3. Right? When I do that, I can rationalize the denominator. Okay, so that's all that's happening with that. Just a little algebra trick to make the numbers more appealing, right? Easier to work with. Okay. All right. Let's do another example. Let's again identify the value of the 6 trig functions, but this time, so let's identify the value of the 6 trig functions, and this time we'll get the angle. So at theta equals pi over 2. Okay, You may be asking yourself, how could I possibly do this? Well, you can't just do this easily unless it's a special kind of angle. So let's draw out the unit circle here again. Now, where is theta equals pi over 2? Right, now if you remember, I mean, I hope everybody's trying to think in radians, but if you're not quite comfortable with radians yet, you can think about this in terms of degrees. So theta equals pi over 2 is what angle in degrees. So if I have pi over 2, I multiply it times 180 degrees over pi, then you'll see that that's equal to 180 degrees over 2, which is 90 degrees. Right, and so this is actually right here, isn't it? Okay, and so what is the value of p on the unit circle at theta equals pi over 2? Well, it's just p is equal to, well, it's 0 on the x-axis and 1 on the y-axis. Okay. All right. So, what's the value of the 6 trig functions here? Well, let's try it. Sine of pi over 2 is equal to y, which in this case is equal to 1. Cosine of pi over 2 is equal to x, which in this case is equal to 0. And the tangent of pi over 2 is equal to y over x, which is equal to, well, it's 1 over 0, right? And so we would say that the tangent is actually undefined at pi over 2. Okay? And what about the secondary trig functions? Okay, so we've got the cosecant of pi over 2, and that's equal to 1 over y, which is 1 over 1, again 1. What about the secant pi over 2? Well, that's 1 over x, and so that would be 1 over 0, and so that's undefined. Right? You can't divide by 0, that's all that's happening there. And the cotangent of pi over 2 is equal to x over y, which would be 0 over 1, so the cotangent is equal to 0. Right? You can divide 0, but you can't divide by 0. Just make sure that you keep that straight. Right, so now we know the sine, or the 6 trig functions at pi over 2. Okay. All right, and so using a similar method, we won't go through all of this, but I encourage you guys to do it. Using a similar method, can you find the 6 trig functions at theta equals pi, 3 pi over 2, and 2 pi? Right, and I'll give you a hint. The hint would be that p is equal to, at pi, p is equal to negative 1, 0. At 3 pi over 2, p is equal to, so that would be 0 comma negative 1. And at 2 pi, p is equal to 1 comma 0. Right, and so just like here, p was equal to 0, 1, and that's the key to finding the trig functions at theta equals pi over 2. At these other 3, you have this one, and this one. Okay, so spend the time and practice and make sure that you can understand that idea, and make sure that you can get to those values. Okay, very good. Let's shift gears a little bit and talk about these functions and some of their properties as functions. Okay, and so we've already said that they're functions, and so that means they have all of the properties of an algebraic function. Right, so these are functions. So specifically, that means they pass the vertical line test. right? Which just means that, you know, a function that passes the vertical line test, it means if you draw vertical lines anywhere on the graph of the function, then then you only intersect the function at a single point. So this would be an example of a function. Now, conversely, if I have something like this, when I draw the vertical lines, then I intersect it in multiple places. So that means this is not a function, right? So these are functions, so they pass the vertical line test. And they're because they're functions, we can also talk about the domain and the range of these as functions. So what is the domain and the range of the trig functions? And so let's talk about sine and cosine in particular. So if sine of theta is equal to y, as we saw, we can see that the value of theta can be basically anything. Basically any real number. Right? There's no number that I can't plug into the sine of theta, right? And you can just see that because whatever I plug in here, it's just going to be equal to the y value. Okay? And so that means that the domain of sine is basically all real numbers. So we'll write it like this. So any real number can be plugged into this sine function. But the range we know is limited. The range is limited, right? Because we know that, right, if we think about the unit circle, okay, so here we're dealing with 1, 0. Here we have 0, 1. Here we have -1, 0. And down here we have 0, -1. Right? And so the sine function is going to top out up here at 1. 1 is the max value of the sine function. And it's going to bottom out down here at -1. Right? And every value in between there is going to be valid for the sine function. So the range of sine is equal to -1 up to +1. Okay? So right in the middle here, you can see that the y value is 0. Somewhere like this, the y value might be 1/2. Right? Y equals 1/2 here. Right? And so you can see it's going to start at 0, and it's just going to go up to 1, and then down to 0, and then down further to -1, and then back up to 0. So it's cyclical. Right? So the range is going to be between -1 and 1. Now, the same thing is true of the cosine. Right? So the domain of the cosine is similarly -infinity to infinity, and the range of the cosine is equal to, same story as with sine, it's equal to -1 to 1. Right, and for the same reasons, right? You can see the sine is the x, right? And so it tops out at 1 over here, and then it shrinks down to 0, and then it shrinks down further to -1 where it finds a bottom, and then it goes back up to 0, and then back up to 1. Right? For the same reason, the range of the cosine is -1 to 1. Okay? Very good. Right? And so these just kind of some basics, and we'll get into the domain and range of some of the other trig functions a little bit later. But we want to start with this one just to kind of get you thinking about these things as functions. Right? So they are functions. You plug in a real number and you get a real number out of it. Okay? And so as such, you need to know what values can you plug into them and what values can't you plug in. Okay. Okay, now let's do a derivation here. And so one of the things we're going to be doing over the course of the next couple of lectures is we're going to be finding the exact values of trig functions. Okay, and so what we've done so far is we know, given the definition that we're working from, we know the exact exact values for, well, really the only one we've done so far is theta equals pi over 2, right? But then I did give you as an exercise about 10 minutes ago to go through and find out for pi, 3 pi over 2, and 2 pi, right? So this is the quadrants, right? So the quarters of the unit circle, right? So what we want to do next is we want to talk through exact values of trig function, of the trig functions at theta equals pi over 4. Okay, what does pi over 4 look like? Well, let's draw the unit circle here. How many circles will I draw in an hour? Many. Okay, so pi over 4 is, if you think about what is pi over 4, theta equals pi over 4 is equal to pi over 4 times, and we want to convert it to degrees, 180 degrees over pi. So 180 degrees divided by 4 is 45 degrees. So again, I want you guys to start thinking about trig, about angles in terms of radians, but if we're still sort of working our way towards that, it's totally fine to convert things to degrees to kind of get a sense for it. But what that basically means is the angle that we're interested in is this one. It's a 45 degree angle, and it's pi over 4. Okay, and so let's put on here, let's put a P, and we're going to call it AB, right, instead of XY. Okay, it is some definite point, we just don't know what point it is yet. We'll figure out what it is in a second. As soon as we figure out what A and B are, then we know the value of the 6 trig functions, right, by the definition. Right, so what we need to do is we need to figure out what these A and B are. Right, so what can we say about this line? Right, remember this is the unit circle, this is the XY plane, right? What can we say about this line? Well, this line here that I've drawn is the line y equals x. Okay, so remember, like this is again algebra and trigonometry are very tightly connected here. So y is equal to x. All that means is if I plug in 1 for x, I get out 1 for y. So if I go over 1, then the line would be here, right, which would be 1 on the y-axis. If I plug in a half, I get a half, right? So halfway over, halfway up would be halfway on the y-axis. So this is the identity function. Right, we've all seen this one a million times. It's the identity function. Okay, so what is this point P equals AB? What is that point? Well, let's think about this. Let's just kind of use what we know. So we know that the unit circle has an equation, x squared plus y squared equals 1. And so we want to know what A is and B, right, on this unit circle. So we can say A squared plus B squared equals 1. Okay. Now, whatever A and B are, because it's on the line y equals x, we know that A and B are the same, right? Because of what I just said here. If I plug in a 1 for x, then I get out a 1 for y. If I plug in an A for x, I get out an A for y. So whatever x happens to be, y is the same thing. So instead of writing a squared plus b squared equals 1, I could just as well write a squared plus a squared equals 1, couldn't I? I could do that. Okay, and so what does that mean? Well, it means that 2 times a squared is equal to 1. Okay, and that's just doing some algebra on this. That means that a squared is equal to 1/2. Right? And that means that a, you can take the square root, a is equal to plus or minus the square root of 1/2. Okay. Now we're talking about the first quadrant, so am I interested in the positive or the negative value of x? Well, it's got to be the positive value, right? Negative would be over here. So I'm interested in just the positive value. So a must equal the square root of 1/2. Okay? And so a better way to write that would be 1 over the square root of 2. And we can rationalize the denominator here. Again, just like we talked about. And you'll see that this is equal to the square root of 2 over 2. Okay, and so a is equal to the square root of 2 over 2. Okay, and consequently, because a and b are the same, because they fall on this y equals x line, that's also what b is equal to. Okay, and so that implies that the point P equals AB is actually square root of 2 over 2, comma, square root of 2 over 2. Okay? And so that's what this is. This is the square root of 2 over 2, and comma, square root of 2 over 2. That's the coordinate of P. Right? And so now we know something about pi over 4. We know that it intersects the unit circle at square root of 2 over 2, square root of 2 over 2. So that means we can just use this guy here to derive the 6 trig functions. Right? So the sine of pi over 4 is equal to y, which is the square root of 2 over 2. The cosine of pi over 4 is equal to x, which is again the square root of 2 over 2. The tangent of pi over 4 is equal to y over x, which is the square root of 2 over 2 divided by the square root of 2 over 2, otherwise known as 1. Anything divided by itself is 1. The secant, well, let's start with the cosecant. The cosecant of pi over 4 is equal to 1 over y, and so that's 1 over the square root of 2 over 2. And so again, you have to kind of sort this out, and that's 1 over 1 times 2 over the square root of 2. And so you get 2 over the square root of 2, and we can rationalize that. And we see that that's 2 over the square root of 2 times the square root of 2 over the square root of 2. And so you get 2 square root of 2 over 2, so you get square root of 2. Okay, now good news is that the secant is exactly the same thing, isn't it? 1 over x is going to give you 1 over square root of 2 over 2 as well, and so we could just write that. And the cotangent of pi over 4 is x over y. It's the same thing as the tangent, isn't it? Square root of 2 over 2 over square root of 2 over 2. So you flip that upside down, it's exactly the same, and so it's 1. Okay, and so here we have the 6 trig values for theta equals pi over 4. Okay. All right. And one thing you can do is you can, on your own, similar to what I asked you to do with the quarters, you can go through and figure out what the other angles are. Right. So if this is pi over 4, then this one here, so if that's pi over 4, then this one would be 1, 2, 3 pi over 4. And then down here would be 1, 2, 3, 4, 5 pi over 4. I'll just write it out here. And then this would be 6, 7 pi over 4. So you can use the same basic approach to figure out the value of the trig functions at these other angles. So use the same, I don't need to write so, use the same basic approach to figure out the value of the 6 trig functions at 3 pi over 4, 5 pi over 4, and 7 pi over 4. It's going to work almost exactly the same way. Right? So you can imagine 5 pi over 4, I'm just going to have negative a and negative b. look the same way. At 3 pi over 4, I'm going to have negative a, positive b, right? So the only thing that's going to change are kind of like the signs, right? But just try to figure that out. It is important that you know these. I'll kind of tell you what they are in later lectures, but it's important that you kind of know where they came from. Okay. Now these are common values, right? The quarters are common values: pi over 2, pi, 3 pi over 2, etc. These are also important values. These are the eighths. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi. These are all values that we'll return to regularly. Okay. All right. Very good. Very good. Okay. So let's shift gears again here and talk about more function properties of the trig functions. And so we have this idea of even and odd functions. Okay, so recall, let me write this out. Recall, a function is even. It's even if f of negative t is equal to f of t. And a function is odd. It's odd if f of negative t equals negative f of t. Okay, so functions can be even or odd. And so what is the so just to kind of help clarify this a little bit more, let's take an example of a function. So if I have like a quadratic function like this, so here's my x-axis, right? And so let's say I have on here I've got t, and then over here I've got negative t, right? So a quadratic function, in this case f of negative t is this value, and it's also equal to f of t, right? And so a quadratic function like this is an example of an even function, right? And so to kind of contrast that, you might have something like this, right? So here again I've got my negative t, and over here I've got my t. And so f of negative t is up here, f of t is down here. And so in this case, f of negative t, but you can see that these are the same values. So maybe 1, 2, 3, 1, 2, 3. F of negative t in this case is equal to negative f of t. Okay, and so this is an example of an odd function. Okay. Right, and so these are even odd functions. Okay. All right. So, what about sine and cosine? What about the trig functions? Okay, so let's just kind of limit it to sine and cosine for now. What about sine and cos? Are they even? Are they odd? Are they neither? Let's see. Okay, and so let's draw a unit circle and reason about this a bit. Okay, let's reason about this a little bit. So let's this is a unit circle. Okay, and let's put in 2 points here. This will be P, and this will be Q. Now notice these are supposed. Well, shoot, I kind of drew that badly. Let me redraw that. I want it to actually look reasonable. Let me redraw. Okay, and so I've got some line here. So let's say I've got P here, and I've got Q here. Okay, and they're right on top of each other, aren't they? And so let's say that this angle is T, then that would make this angle negative T. Okay. Now P, we'll say, is cos of T times sine of T. We know that sine of T is equal to Y, cos of T is equal to X, and so we can put that in there. And Q we can write as cos of negative T sine of negative t. Okay, so kind of based on this drawing, right, we can see that the x coordinates of p and q are the same, right? So the x coordinates are the same. Right? Because this is the x-axis, right? This is the x-axis, and you can see that it cuts through the x-axis at the same value. Right? So that means that cos t is equal to cos negative t. Okay? What does it mean for a function evaluated at negative t to be equal to the same function evaluated at t? It means that it's even. Right? So cosine is an even function. Okay. What about sine? Right, so the y-coordinates are not the same. Right, so the y-coordinates, is one of them's down here, and the other one's up here. Now they do happen to be the same distance though. Right? So the y-coordinates are not the same. So sine of t, well, we'll say sine of negative t, which is this guy down here, that's equal to, well, it's not equal to sine of t, but if I made sine of t negative, it would be equal to that. So it's equal to negative sine of t. Right? And so this means that sine is odd. Right, so the cosine is even, the sine is odd. Okay, and you can easily confirm this if you've done the exercise of going through and finding some of the other values. All right, well, let's just take pi over 2. So cosine of pi over 2. Well, let's do it something. Sine of pi over 2 would be more interesting, wouldn't it? Sine of pi over 2 is equal to 1, and sine of negative pi over 2 is equal to negative 1. Right? And so that means the sine of negative pi over 2 is equal to negative sine of pi over 2, right? Sine of negative pi over 2 is equal to negative 1, and sine of pi over 2 is 1, so that's negative sine of pi over 2 is negative 1, right? So that's true. Okay, and so this kind of demonstrates that the sine is odd. Right, you can do the same thing for cosine, except let's do cosine at let's say cosine of 180 degrees. So cosine of pi is equal to negative 1. Okay, and cosine of, well, that's not a good example either. Now, we'll skip that example. Well, no, we can do it. Let's say cosine of pi over 4. Cosine of pi over 4. We just did that one, didn't we? Cosine of pi over 4 is equal to the square root of 2 over 2. Okay, and what is the cosine of negative pi over 4? Well, we didn't do that one in class, but if you spend the time to look at that, it's the same as 5 pi over 4, right? And you'll find that that's equal to the square root of 2 over 2 as well. Okay, and so that means that cosine of negative pi over 4 is equal to the cosine of positive pi over 4. So they're the same, right? And that's due to the evenness of the cosine. Okay? Okay. All right, so let's kind of summarize all of that here. What can we say about that? It's a summary. All right, so to summarize, the cosine is even. Okay, cosine is even, and because the secant is the reciprocal of the cosine, it's also even. Okay, so secant of theta is also even. And just spend a few moments thinking about why the fact that they're reciprocals would mean that if one's even, the other is even. I think you'll be able to see that one pretty quickly. Right? So what does that mean? It means that the cosine of theta, cosine, there's different ways to write. I want to make sure I'm writing it the same way each time. So cosine of negative theta is equal to the cosine of theta. And it also, we know now that the secant of negative theta is equal to the secant of theta. Right, so that's the first takeaway. And then secondarily, the sine of theta is odd. Right, so the sine is odd, we saw that, we derived that. And the cosecant is the reciprocal of sine, and so the cosecant of theta is also odd. Okay, cosecant is also odd, and so what we can see here is that sine of negative theta is equal to negative sine theta, and cosecant of negative theta is equal to negative cosecant of theta. Okay. All right. And it turns out that the tangent and cotangent are also odd, right? And kind of, there's different ways to think about this. Probably the simplest way to get to that fact is that we haven't really talked about it yet, but the tangent can be thought of as a composition of cosine and sine, not a composition, but a division, a ratio of the two. And the cotangent is as well. So if you've got an even and an odd function multiplied together, the result is going to be odd, right? And so consequently, tangent of negative theta is equal to negative tan theta, and cotangent of negative theta is equal to negative cotangent of theta, right? So they go together, right? So you've got 1, 2, 3, 4 odd functions, and 5 and 6 are even. So you got 2 even, and you got 4 odd. Okay. All right. Okay. All right. So we're going to kind of jump into another topic here, and this is a topic that we'll be exhaustively looking into as the course goes on. But there's a very large number of special relationships that exist among the trig functions. It's kind of mind-blowing. As you get into it further and further, you see that there are just more and more of them. And so we'll be looking at all of them. Well, not all of them. We'll be looking at a bunch of them throughout the course. We're going to kind of start with the most fundamental relationships, though. And hard to know exactly what to call them, so I'm going to name them like this. So you've got what I'm going to call the quotient identities. Okay, the quotient identities, and that one is that the tangent of theta is equal to, well, we saw that the tangent of theta was what? It was y over x, wasn't it? Right, and we know that y is equal to the sine and x is equal to the cosine, and so the tangent of theta is equal to the sine of theta divided by the cosine of theta. Okay, so this is one of the quotient identities. The other one is the cotangent, and it's just the reverse, right? So cotangent is x over y, and so it's equal to the cosine of theta divided by the sine of theta. Now, you will use these all the time. These will come up practically every lecture going forward. Right? So they are extremely fundamental. And they'll come up later when we get into verifying trig identities. You'll use these all the time, right? When we get into solving trigonometric equations and law of sine and cosine, we'll use these all the time. So they're extremely valuable and extremely fundamental. The good news is that they're also very elementary, right? It's almost obvious, almost self-evident. If you recall how we define sine and cosine, this is almost like too obvious for words. Okay, and so that's the first identity that we want to draw attention to. The second one is what's called the reciprocal identity. Okay, and the reciprocal identities, we've kind of hinted at these already, right? And for example, we've said that the sine of theta is equal to y, and we said that the cosecant of theta is 1 over y, right? So if you kind of take those two things together, so the sine of theta is equal to y, and the cosecant of theta, it's a c, is equal to 1 over y. Those two together imply that the sine of theta is 1 over cosecant. Right? So how could we get to that? Well, we could take this guy here and multiply both sides by y and divide both sides by cosecant. And so you can quickly see here that y is equal to 1 over cosecant of theta. Right? And then it's just a matter of kind of marrying those two statements together. And so the identities are as follows. Right? So you've got the sine of theta is equal to 1 over the cosecant of theta. And so also you've got the cosecant of theta is 1 over sine of theta, right? So that would be just algebra to get from one to the other. The cosine of theta is equal to 1 over the secant of theta. And similarly, the secant of theta is 1 over the cosine of theta. And again, for the same reasons, you could use the same derivation. And the tangent of theta is equal to 1 over the cotangent of theta. And the cotangent of theta is 1 over the tangent. Okay, so you've got these 6 reciprocal identities. Right, so this is a way of writing a trig function in terms of another trig function. Okay, and this can be extremely helpful as we're working through identities and trying to solve different trig functions. Okay, let's do an example where we make use of some of these identities. Let's try an example here. Okay, so let's say, given that the sine of theta is equal to 2/5 and the cosine of theta is equal to the square root of 21 over 5. Find the other 4 trig identities. Find the other 4 trig, we'll say trig values. Okay, so let's start. So we're given the sine and we're given the cosine. Right, so the tangent can be found by using the quotient identity. So we know the tangent is equal to the sine over the cosine. Right? That's the quotient identity. And so that means the tangent must be equal to 2/5 divided by the square root of 21 over 5. Right, and we can figure out what that is by just kind of multiplying these together, the reciprocals. And so we get 2 over the square root of 21, and so that means it's 2 times the square root of 21 over 21. Okay, and so that's the tangent. And what about the cotangent? We can do that one quick. It's just the cosine of theta over the sine of theta. It's the same story. Right, and so it's really going to be the same numbers as this, just upside down, which means it's going to be the same numbers as this upside down. So it's really just the square root of 21 over 2. Okay. What about the cosecant? Why do I keep writing the cosecant of theta? Well, the cosecant using the reciprocal identity is equal to 1 over the sine. Right? So it's equal to 1 over 2/5, right? And so that's equal to 5/2. Okay, and then finally the secant, well, that's equal to 1 over cos, right? And so the cosine was 21 over 5, so 1 over the square root of 21 over 5. And so it's 5 over the square root of 21. And that means it's 5 times the square root of 21 over 21. That's the secant. Okay, perfect. Perfect. So that's an example of how you can use those identities. They have so many uses. That's just one example, just to kind of give you a flavor of it. Okay, let's talk about another very famous identity. Right, and so let's kind of derive this a little bit. Let's consider x squared plus y squared equals 1 of the unit circle. This is the equation of the unit circle. Okay, so consider this equation, which is the equation of the unit circle. Right, so it follows, like just kind of plugging in the definitions, it follows that, so x is cosine, so instead of x squared plus y squared equals 1, we could write cosine squared theta plus sine squared theta equals 1. Okay. And just as a point of interest here, because this may be the first time you're seeing this, when we talk about, so x squared, right, here what we're doing is we're taking x squared, this is an aside, right, x squared equals cosine theta squared, right? So just notationally, this is slightly cumbersome. So what people will do is they'll write it like this instead. They'll kind of square the cos piece and just put the theta there. It means the same thing as this. It's just notationally a little bit more convenient because you don't have to put parentheses. Cosine, sine, all of those trig functions are constantly being squared and being raised to powers, etc. And so this is a notation that has kind of developed over time to make that task of writing it a little bit more convenient. Okay, so when I write cos squared theta, I just mean cosine of theta, the value of that function squared. Okay, right, and so just the fact that we have the equation of the unit circle, and if I just substitute in cos for x and sine for y, then I get this guy here, and this is a very important identity called the Pythagorean identity. It's the Pythagorean identity. Obviously, this is derived from the Pythagorean theorem, which says a squared plus b squared equals c squared. And we'll see later when we get into right triangle trigonometry, we'll see how this can all be derived from right triangles. But this is the Pythagorean identity for cos and sine. Right? And so there's actually 3 parts to this. There's cos squared theta plus sine squared theta equals 1. That's the one we just saw, and we can see where that comes from. There's also a version for tangent and secant, and so it says 1 plus tan squared theta equals secant squared theta. And then there's also a version of the Pythagorean identity for cotangent and cosecant. So it says 1 plus cotangent squared theta is equal to cosecant squared theta. Right, so these 3 comprise the Pythagorean identities. Pythagorean identities. Okay. The latter 2 identities, right, so namely these 2, they can be really easily identified using just they can be identified using just cos, the first one, right? So let's just see how we can do that, right? So for example, right, if I say 1 plus tan squared theta equals secant squared theta, where's that come from? Well, 1 plus tan squared theta, well, tangent is sine over cosine, so this is equal to 1 plus sine squared theta over cosine squared theta. And you can get a common denominator here, and you'll see that that's cosine squared theta plus sine squared theta over cosine squared theta, right? So multiplying, just kind of moving this denominator over to this term. Okay. And so that is obviously 1, so that's equal to 1 over cos squared theta. And then what is 1 over cos squared theta? Well, it's just it's just the secant squared theta, right? That's just again, that's the reciprocal identity at work here, right? So here you use the quotient identity on the tangent, right? And then here you use the reciprocal. So this is the quotient, and this is the reciprocal. Right, and you can do the same thing for the one involving cotangent and cosecant. Okay. All right. Here's an example. Let's do an example using that. So if sine of theta is equal to 3/5, right, and we'll put a range on theta here, and we'll say that theta is between 0 and pi over 2, right? What does that mean? Well, it just means that theta's got to be somewhere up in this quadrant, right? Okay. So if sine of theta is 3/5 and theta is between 0 and pi over 2, let's try to figure out what the value of cosine of theta is. This is kind of a little bit tricky, except in context we know we just learned about the Pythagorean identity, so probably we're going to use that. So sine squared theta plus cosine squared theta equals 1. And so we know sine, we're given sine, so that implies that 3/5, that's what sine of theta is, we got to square it, plus cos squared theta equals 1. And so this is like a little equation we can solve, right? So cosine squared theta must be equal to, well, it's 1 minus 3/5 squared. Okay, and what is that? That is 1 minus 9 over 25. Right? We can kind of do that math in our head if we want. 25 minus 9 over 25. It's also totally acceptable to pull out a calculator if you want, but you could see that that's 16 over 25. Right, and so cos squared theta is 16 over 25. Those are nice square numbers, aren't they? That's great. And so that means that cosine of theta is equal to plus or minus the square root of 16 over 25, which is plus or minus 4/5. Okay, and so it's one or the other. It's either 4/5 or negative 4/5. So which one is it? Is it 4/5 or is it negative 4/5? How can we tell? Well, that's where this comes into play right here, right? So what that's saying is that the angle is over here somewhere. Sorry, let me bring that up a little bit more, right? So if 0 is less than or equal to theta is less than or equal to pi over 2, that means it's got to be in this quadrant, right? So it's somewhere in here. So basically this is all off limits. Well, is cosine positive or is it negative over here in this quadrant? It's positive, right? Definitely positive, right? It's definitely positive. So cosine of theta must be equal to 4/5, right? Because we're in the first quadrant and cosine is always positive in the first quadrant. Okay? All right, very good. Okay, we're getting very close to being through this section. I have one more topic to hit up, right? And that's the idea of a periodic function. Okay, so let's remember what that means. A function f is periodic, right? It's periodic if, well, you can kind of think of periodic as meaning that it's a function that repeats itself, right? It's a function that repeats itself. But what it means kind of more technically is that a function is periodic if there exists a positive number p such that f of theta plus p is equal to f of theta. And this can't be true just once, it has to be true for all theta. For all theta in the domain of f, right? So p is a fixed number that works for all theta, right? What it basically means is if I have a value of theta and I evaluate it at f, then whatever that happens to be, I just have to go out p. I just have to move forward or backwards, depending on what p is, and I'll get the same value, right? And this is going to work for all theta in the domain, right? It's all going to be, you'll get the same value if you move forward by p units, okay? And so the trig functions are periodic. Well, sine and cosine are periodic. Sine and cosine are periodic functions, right? And this will become very clear when we start graphing these functions, but we're not quite ready for that yet, so we just want to kind of talk this out in more general terms. So an example here of this, and we can kind of see this through this example. Sine of pi over 2 is equal to 1. Okay, we know that. Sine of pi over 2 plus 2 pi is also equal to sine of 5 pi over 2 is equal to 1 as well. Right? And I could go further. I could say, now sine of 5 pi over 2 plus 2 pi is equal to sine of 9 pi over 2, which is equal to 1 as well. All right, so you can see the value of the functions are all equal, and we're adding 2 pi each time. Right? So from this example, you can see that sine repeats itself every 2 pi. Now I'm going to put that in air quotes, repeats itself every 2 pi, right? And so we say that 2 pi is the period of sine. Right? It's the p that we defined up here, right? So whatever theta happens to be, if we add 2 pi to it and it's a sine function, then we'll get the same value every time. Right? This goes back to the idea of coterminal angles, right? So if an angle in standard position has the same terminal side, then they're called coterminal. So obviously they're going to also have the same value of sine, right? And as it turns out, you're going to have the same value of cosine. Okay, so the same thing is true for cos. Okay, cosine and sine are both periodic, and they repeat themselves every 2 pi. Their period is 2 pi. Now it turns out that tangent and cotangent are also periodic, but they have a different period. So tangent and cotangent are also periodic functions, but their period is pi. Okay, it's a smaller period, shorter period. Okay. And so we can use this fact to find exact values. And so let's do, this will be kind of the last example, but let's do one example here just to kind of drive this idea home. And we'll come back to periods again as we move through the course, but here's an example where we make use of this. So let's find the exact value. Let's find the exact value of sine of 9 pi over 4 and tangent of negative 5 pi over 4. Okay, so that's the ask. Let's find the exact values of these two. And so we don't have any idea how to find these directly, right? We've not done this. We've looked at exact values for pi over 4 and all of the other eighths, and we've also looked at the exact values of the quarters, right? But so how could we do this one? Well, one of the things we can notice here, let's start with the sine. So sine of 9 pi over 4, well, that's actually equal to sine of, right, if you look at this angle, it's equal to pi over 4 plus 8 pi over 4, right? I mean, that's just two fractions. You add them together, you get 9 pi over 4. But it's very convenient, right, because pi over 4 is a value that we know the sine function of, and 8 pi over 4 is the same thing as 2 pi. You can reduce that. Right, so this is just the sine of pi over 4 plus 2 pi. Right, and we just got done saying that sine is periodic with regard to 2 pi, that's its period, and so that means it repeats itself. So basically what we're saying is that whatever sine is at pi over 4, because sine is periodic with period 2 pi, sine of pi over 4 plus 2 pi is going to be the same. And so we know that the sine of pi over 4 is equal to the square root of 2 over 2. Right? And so the sine of 9 pi over 4 is going to be the same. Okay, so just keep in mind we derived this earlier in the lecture. Right, so just an aside there, just to make sure you know where that came from. Just flip back a couple pages in your notes and we talk through that. What about the tangent example? So tangent of negative 5 pi over 4. We're going to use the same kind of trick, right? So first of all, the fact that it's negative is not, it just makes the reasoning a little mushy. So let's use the fact that tangent is an odd function to rewrite it without the negative angle. So tangent of negative theta is equal to negative tangent theta. So this would be negative tangent of 5 pi over 4, right? Earlier we talked about even odd functions. Tangent's an odd function. Right? And then we can use the same trick on this angle. So negative tan of 5 pi over 4 is equal to pi over 4 plus 4 pi over 4. Right? So that's negative tan pi over 4 plus 4 pi over 4 is just pi. Right? And so we just got done saying that tangent is periodic with period pi, right? And so this is going to work out nicely as well. And what is the tangent of pi over 4? Well, if you look back earlier in the lecture, you'll see one of the examples. We talked about what the values would be at pi over 4, and we saw that tangent was square root of 2 over square root of 2, square root of 2 over 2 divided by square root of 2 over 2, so it was actually 1. And so that means this is equal to negative 1. Okay. All right. And so that is that example. So using even odd functions and also using the periodicity of the functions. Okay, and then let's just kind of summarize this period business. So in summary, just to have this, the sine of theta plus, now the period is 2 pi, and then we can multiply that by n, and we're always going to get the same value for the sine. Right, so if you know the value of sine theta, then you know the value of sine of theta plus 2 pi. Any add on 2 pi times n, and you know the value of those angles as well. And the same thing is true for the cosine. Okay, and something very similar for the tangent. Tangent of theta plus pi times n is the tangent of theta. Okay. Okay, and so that's kind of a summary of the period properties of sine, cosine, and tangent periodicity. Okay, and so I think that's where we'll stop with this section. And so in the next section, we'll take up the definition of the trig functions from a slightly different angle. All of these are connected, but we'll take it up from a slightly different angle, and we'll look at right triangle trigonometry. So that's where we'll leave it, and take care, everybody, and we'll talk to you next time. Take care.